Today we are going to take some more problems based on infinite groups. Infinite group means a group will contain infinite number of elements. So, for example, this is our first problem and we have to prove that the set of all integers is an abelian group with respect to addition. It means we will take here all integers from minus infinity to plus infinity, all negative and all positive integers. So, we have written a set Z having all integers from minus infinity to plus infinity, and now we will wish to prove that this set Z is a group with respect to addition. Student, please note it very carefully. If your set has infinite number of elements, then you will not create composition table, because we can't create a composition tables having infinite elements, and we can't implement such table with having infinite number of elements in our problem. So we will justify all 5 properties because we have to prove that this is abelian group. So these 4 properties, 1, 2, 4, these are related to group, and this is commutative property. This is the additional property which we have to prove for abelian group. Okay, student, we will first we will see about the closure property. If we take any integer, let us take integer 5 and one more integer, suppose I am taking -3. If I operate this 5 on -3, then I will get 5 plus -3, that is 5 minus 3, and this result will be equal to 2. This is again an integer. It means if we take any two elements A and B and we take their sum, then the resultant will also belong to this family, and the family is the integer family. So it is obvious that our closure property is satisfied here, because the sum of every two integers will be always an integer. It can't be float. Second is identity axiom. We know that here we are trying to prove that G is an abelian group with respect to addition. Student, please note it very carefully that 0 is always an additive identity while 1 is the multiplicative identity. If you have to prove any set of elements as a group with respect to multiplication, then you will focus on 1, because 1 is the multiplicative identity. But if you are taking you wish to prove that our set is a group, then you will, with respect to addition, then you will take 0 as an identity. So we know that 0 is always belongs to a set of all integers. So we can directly say that identity axiom is also satisfied, because 0 is the identity for every integer. Inverse axiom. Now we want to prove that every element has its own inverse. So 0 is the identity. Suppose we have 0 and in 1 and 2 and -1 and -2 and so on. Suppose we want to check their inverse. What number must be added to +2? Obvious, it is -2. If we add +2, -2 in +2, then we will get 0. So -2 is the additive inverse of +2. Similarly, for this one, we will add -1 and we will get 0. So -1 is the additive inverse of 1. 0 plus 0 equal to 0. It means 0 is its own additive inverse. If you add +1 into -1, then you will get 0. It means the additive inverse of -1 is +1, and similarly the additive inverse of -2 is equal to +2. So in this fashion we see that every integer has its additive inverse, and this is also an integer because this set of elements contains all integers. If +2 is available in this set, then -2 will be also available in this set. If minus 2 is available in this set, then plus 2 will be obviously available in this set. So we can say that the additive inverse of each element is available in this set G. Now the fourth property is associative property. We know that the integers good hold associativity. You can check it on any three integers. Suppose I am taking here 2 and I am taking here 7 and the one more integer is 5. Suppose first I add 2 and 7 and after that I am adding here 5. We get 7 and 2 and 7 9 and 9 plus 5, this is equal to 14. But if I apply associativity here, I change its addition pattern. I am adding first last two elements. It means these two elements. Then I get 2 plus 7 plus 5. This is equal to 12 and this is equal to 14. This is again 14. So we can say that integers good hold associativity. Similarly, we can say that integers are good hold commutativity with respect to addition. You can apply this operation on any two integers. Suppose I am adding 1 and 4, then the result will be obtained similar to the results which will be obtained by 4 plus 1. So integers good hold associativity, integers good hold commutativity. A student can write this statement directly, that the set of all integers or a group of integers good hold associativity and every two integers good hold commutativity. Assume since this set G satisfy all these five properties, so we can say that the set Z is a abelian group with respect to addition. Let us see one more problem based on infinite group. Here the problem is we have to prove that the set of all even integers. Please note that now the set will contains only even integers including 0. It means we can have 0, we can have 2, we can have 4 and so on, and in opposite side we can have -2, we can have -4 and so on. So this is our set of elements. Now we wish to prove that this set is a additive abelian group. So first we will see the closure property. We can write here the sum of any two even integer will be always even. In this student, please note it, 0 is neither negative nor positive, but in this question it is written that including 0. So it means we can include 0 as per the instruction given in the question. Suppose I add any two even integers, then result will be always even integer. Let us I add 2 plus 8. Here 2 is an even integer and 8 is always even integer. The sum of 8, 2 and 8 is 10 and 10 is also an even integer. So we can write it directly that the sum of every two even integer. Please correct it. Note here, this is even integer. Set of every two even integer is also even. And in our second statement, we know that 0 is also available in this set. So we can write it directly that 0 is available in our set, and we know that 0 is the additive identity for every integer. So 0 will be always 0 will be obvious an additive identity for even integers. Now for third case, inverse axiom. Let us take any positive even integer. Suppose I take 4. What must be added in 4 to get 0? It is obvious that we have to add -4 will be equal to 0. So a student can justify this result by the statement, and the statement can be written as the additive inverse of a positive even integer will be its similar negative even integer, and the inverse of any negative even integer will be similar positive even integer. It means numerically number and its inverse will be same. As 4 is an even integer which belongs to our set, then obviously minus 4 is an even integer and it will also belongs to our set. So we can say that the inverse of every element is available in Z. So inverse axiom satisfied. Again, these two statements will be written as similar as previous problem. Here we will write that the even integers would hold associativity. It means you can take, for an example, you can take any three set of any three even integers. Suppose I am taking here 2 and 4, and again I have minus 2 or minus 6. Suppose I have minus 6, and we have to add these three elements. Now for associativity, first we can find the resultant of from these two integers, and after that we will add it in this. 2 plus 4, this will be equal to 6, and 6 plus minus 6, it will be 6 minus 6, that is 0. Again, if we add these two elements, then 4 plus minus 6, that will be minus 2, and 2 plus minus 2, that is 2 minus 2, which is again 0. So we can say that the set of integers would hold associativity. Similarly, we can write the set of even integers would hold commutativity. So directly we can write that the set of even integers including 0 will be an additive abelian group. I am repeating again, in case of infinite number of elements, if your set has infinite number of elements, then student will not create composition table, because we can't utilize such composition table having infinite number of elements to justify our problems. In our next lecture, we will take some more problems based on infinite group, such as the set of a group having complex numbers, etc. So that problem will be discussed in our next lecture. Thank you.